Okay, let's take a look at the data sheet that covers our analog to digital converter. We've got 5 inputs for our 16F876 because it's a 28 pin device. We're only going to be using one input. The analog input charges a sample and hold capacitor. The output of that goes to the converter. The converter generates a 10-bit result via successive approximation. Therefore, it requires a clock. It's got high and low voltage reference inputs, external and internal. We're going to be using the internal VDD and VSS. The AD converter works in sleep mode. That didn't really concern us. There's 4 registers associated with the ADD module. That's the result register, AD res, high and low, and 2 control registers. So let's look at AD con 0. First thing we see is clock selection, and we're going to use FOSC divided by 32. The next bits are channel selects, and this selects one of the analog inputs that are configured, and they're configured elsewhere in AD con 1. This just selects a channel that is configured to be an analog input. Then there's the go done bit. You set the go bit to 1 to start a conversion, and you wait for it to go low, and that signals you that the conversion is complete and the result is ready. Then there's AD on, which turns the converter on and off. The AD con 1 register, we're interested in this ADFM allows you to select left or right justification in your result register. We'll look at that in a little bit. PCFG 0 to 3. This selects which analog inputs are configured to be connected as an analog input to the converter. We're just going to use one channel, AN0, and you have the option here to make its reference external or internal. So we're going to use the external reference, VDD and VSS, so we're going to write a value of hex E, or 14, to these 4 bits. Here's a block diagram. Well, this section explains how you do the setup and configuration. We'll be going over that when we look at the code in a minute. Here's a block diagram of roughly what's going on. Here's your channel select bits. It closes value on here, closes one of these switches and makes that channel connected to the AD converter. The PCFG 0 through 3, it shows how it connects to the external or internal references. It doesn't show that it also selects which one of these channels are included in the AD converter input group. But we looked at that just a minute ago. There's some requirements for when you do a conversion and time to wait to do a conversion. This all involves basically when you change one of the CHS bits and you connect a different channel, you have to do this acquisition time. Since we are not changing the channel, we're just selecting channel AN0 as our input. We're just selecting it one time. It's going to remain connected to the whole time. This acquisition period doesn't apply to us, except maybe for the first acquisition, but I know we beat it because there's plenty of other setup we're doing, and we're writing the prompt to the display, and so we easily meet the acquisition time. Here's an input model for what's going on inside the chip. And then selecting the AD clock, we're just going by this table. At 20 megahertz, we're above 5 megahertz. We're not quite to 20 megahertz at the 16 megahertz we're running at. So we're going to use 32 TOSC, which tells us to put a 10 in ADCS in the AD-CON register. And this is more about configuration, setting the A port up correctly in the tri-state control for the A port. We're going to cover that in the code. Here just shows how the AD conversions are done every clock cycle that's required to do it. We just set go, wait for done. All this happens while we're waiting for done to go low. Here's our result registers, 10 bits. Remember we said we're going to left justify it. ADFM equals 0 for left justification. So that means our AD-Res H register will hold the upper 8 bits. AD-Res L will hold the lower 2 bits. AD operation during sleep. It's got that capability. We don't have to worry about that. Alright, let's take it to code to drive our analog to digital converter. First thing we need to do is configure port A. Everything's going to be inputs except for the debug pin, which will be an output. So we'll just go ahead and configure the tri-state control as a hex 3D, and we'll also set the debug pin low and everybody else default right of 1 to all the other pins. And take a look at configuring the ADC. Here's AD-CON 0. We want to turn the analog to digital converter on. We're going to use channel 0, so this CHS pins will be 0. And we're selecting the FOSC divided by 32 clock. So that gives us a hex value to write to the AD-CON of 081. AD-CON 1, we want to left justify the result. So that it's a 0 for ADFM. And to set up our PCFG, we're configuring RA0 as an analog input, and we're using the internal reference, VDD and VSS. Now, one thing I meant to mention when I was doing the going over the PDF file was that when these are all 0, which is the power up default condition, this register is all 0, and all 0 is all analog for port A. And I've messed around a lot of times and not realized that, and tried to use them as digital outputs. I think digital is something like, I forget, I think it's like a 1000 or something like that. Anyway, port A defaults to analog. If you want to use it as digital, you have to configure these 4 bits. Okay, now the driver, when we're through with setup, the last thing we do is start a conversion by setting the go bit in AD-CON 0. It starts the acquisition, and we fall into our main loop. And all our loop does is cycle through here and check for the done. That's the same bit to go low in AD-CON 0, and that shows that our conversion is finished. Now we're going to take the radar values out of AD-Res L and H, and we're going to put them in a couple of general purpose registers, ARL image and ARH image. We're also going to use meter, and which is another general purpose register, and C digit is going to count our subtracts for our successive subtraction algorithm. And we start off, we use this is kind of a goofy 8-bit subtract. We have 10 bits to subtract, 10 bits to use on an 8-bit machine, and I'm not a mathematician or anything. I looked for code that would do 16-bit or 10-bit, but I didn't find anything very useful. So this is what I came up with. And basically at first all I do is pay attention to the upper 8 bits, and if you divide 255 by 5 volts, you get 51. So I just, for the first step, I just divide the upper most significant 8 bits by 51 using successive subtraction. After we run through that, we find our value ends up, we have our count in C digit, and we turn C digit into an ASCII value, and we store it for display. And we also, the next character is the decimal point, so we store that also. Now we have to get, we can get the residue that's in ARH image, and get our 2 least significant bits that we ignored, and put those in ARH, get everything in ARH image, and that's what these shift lefts do. The next thing, now we can work on that in the closest value. This doesn't necessarily evenly divide into into the residue we have left, but 21 is the closest value that I could come up with. And we basically do the successive subtractions again, counting each subtraction in C digit, and when we've reached, we run it down to 0 or less than 0, we form that into a ASCII byte and store that. Now what's left over in for the hundredths bit can be more than 9. So all I do is just strip off anything bigger than 9 and display that. So there's another little source of error. And but anyway, I think this seems to get us close enough to a value. Probably wouldn't use it. Probably wouldn't use it in for anything you need to do accurately. Probably take this ADC data and ship it over to a PC or something and actually process the data there, or find a good library that can do this code. So anyway, after we have saved all our characters, ASCII characters, we display it, and then there's a long delay to make sure everything settles down signal-wise, and then we set the go bit in AD con register, and go back to dim loop and wait for it to be done. We just do that over and over again. So okay, well, let's check out the displays and see what this looks like. Okay, let's fire up and see how we did. And it looks like it's counting up. Got 1 volt, 2 volts. Looks like there's a little jitter on the most significant bit. See if that most significant bit doesn't flick back and forth. Yeah, a little bit between 3 and 4 there. Let's see if we hit 5. Okay, it was 5 there just for a second. So it looks like we're measuring the full range. That's not too bad. It looks like the tenths bit is also jittering back and forth a little bit. I don't know if that's the part of the division algorithm, or actually have some noise on our integrator line. You might want to do some tests and change this up where it does puts out a steady value, and you can measure it with a DMM and compare values. That'd be a little project you could do on the side. But this looks fairly good for a crummy division routine. Okay. Well, at least it works. We know we can program a PIC. We know we can get the PWM working. And we know we can get the analog to digital converter measurements working. Kinda, maybe. Okay, not too bad. Okay, we got our DL1414 display here, and we're taking our ADC measurement. Let's see how she looks. So I hope this is coming out on the camera okay. It's counting up alright. There doesn't seem to be as much jitter on the most significant bit. See if it hits 5 here. Yep. And the 10th bit, there's a little jitter time to time on that. It doesn't seem as much jitter on the bits as with the parallel LCD display. I wonder what the cause of that is. I would have thought this display would be faster and show a little more jitter, if anything. Maybe you have to look into that. Anyway, it's handling our ADC output pretty well. Okay, looks good. And let's take a look at our parallel display. We'll turn her on and see how it displays the readings. Counting up as we expect. It's addressed just about like the parallel display. Did I say this is the serial display? I think I might have said parallel. This is the serial. It's addressed. The lines are addressed the same way. You can see we got on this one lines 1 and 3 have the data on them. If you have a 2-line display without any code change, this should appear on lines 1 and 2. See, counting up, it looks like see if there's 5. Yep, just for a second there. I don't really see the jitter on the 1's position or the 10's position. That's odd. Huh. It's kind of a mystery what's going on. I can't explain that, why we saw so much jitter on the parallel display. Maybe it's adding noise to the system itself. I don't know, that's interesting. If we ever get to really doing ADC measurements for accuracy, we'll go over more of the parameters that are required to read a stable voltage. Using the external voltage reference for ADC will help a lot. And in this case, we have you can get a 4 volt reference and make it evenly divisible. Your divisor 1024, make it evenly divisible by that, and the math is a lot easier and a lot more accurate. But this looks pretty good. I see this block showing up in the least significant bit. I think I left out a check for overflowing. I left out the check for overflowing the least significant bit. So you can apply that from, I'll fix that in the code, and then that'll be usable. Okay, well, pretty good. Kind of happy with that, sort of.